In this video, we'll discuss ensemble methods for deep learning. Creating ensembles of multiple models is a classical tool in machine learning to reduce overfitting. And here we'll see several specialized ways for creating such ensembles in deep learning. Let's dive right in. Ensemble methods. One very popular type of approach for building ensembles in the machine learning literature is called bagging. Bagging is short for bootstrap aggregation, and it works as follows. So you draw different types of bootstrap samples of your training data, and then you train models on each of them. Now, what is a bootstrap sample? It is given a data set. In order to generate a bootstrap sample like this here, for each of the data points in here, you draw a uniform random sample from your original data set, and you do that with repetitions. So it is very possible to get copies 1, 2, 3, 4 of a given single data point and have other data points not occur at all in a bootstrap sample. And so we draw many of these bootstrap samples. In this case, we have visualized 3 of them, and they are quite different. And since they are quite different and we fit a classifier on each of them, the classifiers are quite different. And different classifiers, these different classifiers then make different predictions, and in particular, they make different errors. So, and well, there is a theoretical result also due to the author of this bagging paper, Leo Breiman, that computes the overall generalization error of an ensemble in terms of the individual strengths of each of the models and the degree to which the errors that are being made by the ensemble members are uncorrelated. And if your individual models are good and they make uncorrelated errors, then you overall get a very good performance. Now, you want diversity between your models in order to get that uncorrelated errors, and you want them to be good. Relating this to the bias variance discussion we looked at before, since we're drawing these bootstrap samples and we're not fitting models on the original data, we actually introduce some bias. But by actually aggregating across these different models with diverse predictions, we reduce the variance a lot. And so typically bagging improves performance quite a bit. In deep learning, however, bagging is actually not that popular. One reason for this is likely that we don't really need the bagging part in order to actually obtain diverse models. We can simply rely on the stochasticity of stochastic gradient descent. Because if we actually run stochastic gradient descent on the same neural network with the same hyperparameters many times, it will yield different local minima. And these local minima tend to actually be quite diverse and to make uncorrelated errors, which is precisely what we need in an ensemble. And then, like in bagging, we would aggregate the output by, for example, averaging them. Now, deep ensembles, in contrast to bagging, do not actually introduce bias, but they reduce variance. So this is great. Of course, there's also downsides, namely if you actually afford ensembling K models, then well, this does yield a K-fold increase in complexity for the training time, for the prediction time, and for the storage requirements. So while you actually get better performance, it doesn't come for free in those dimensions. These deep ensembles actually do perform surprisingly strong, and particularly strongly so for the tasks of uncertainty quantification and performance under data shift. So uncertainty quantification, if your models make different predictions, then you're uncertain. If they make the same prediction, you're certain. And you can actually use this very simple empirical estimate of uncertainty to quantify how uncertain you are, and it's actually quite well calibrated. And performance under data shift is what's actually visualized on this slide here. So dataset shift means that your test distribution is not identical to your training and validation distribution. And one way in which you can, for example, have a shift in datasets is visualized on the right in this benchmark ImageNet C. And in ImageNet C, you have different types of corruptions for your data. For example, you have things like speckle noise or Gaussian blur or spatter, or you change the saturation, and so on and so forth. So there's these different ways in which you can corrupt your image and in which you can then shift the entire distribution of your data. And these deep ensembles actually do yield surprisingly strong performance, not only under uncertainty quantification, but also for performance under this data shift. So if you train on the original ImageNet and then you test on ImageNet C, they're actually doing surprisingly well. So even though deep ensembles work surprisingly well for uncertainty quantification and robustness under data shift, ensembles can be improved even further by actually increasing the diversity of our ensemble members beyond what can be achieved by stochastic gradient descent. And one way to do this in particular is to actually use different hyperparameter settings for the training pipeline in the individual ensemble members. The resulting approach is called hyperdeep ensembles. And basically in hyperdeep ensembles, you carry out some hyperparameter optimization run, and then you can directly reuse the evaluations from this hyperparameter optimization in order to build an ensemble. And this is an approach that we've actually previously used in our paper on AutoSCLearn. The first author is Matthias Feurer, a PhD student of mine. And this was done in 2015 in the context of non-deep learning, but this actually has now been shown to directly carry over to deep learning and to in particular also yield really good performance for this robustness under data shift. We've also extended this to look at increasing the diversity of our neural networks, the individual ensemble members, by actually using different neural architectures for the different ensemble members. And this approach then is called neural ensemble search and achieves very, very nice diversity results and also, again, very good performance for uncertainty quantification and robustness under data shift. Now, while all of the previous methods I talked about were costly in terms of building the ensemble, so if we wanted k ensemble members, we would have an overhead of a factor of k. This is not the case for the approach of so-called snapshot ensembles. So this works as follows. You basically run SGD with restarts, something we saw before in our previous lecture, which basically had these cosine annealing phases of iterative convergence. And then what you do is you take snapshots of the weights before each of the restarts. So right after your learning rate has converged to 0 and you're about to restart, you actually take a snapshot of the weights, save them away, and then in the end, you ensemble these different snapshots. And if you run this approach with something like 3 snapshots, then you actually get similar performance as deep ensembles get with 3 ensemble members. So the history actually of this paper was very interesting. Snapshot ensembles were introduced by Huang et al., based on a previous archive paper in which we had shown this SGD with restarts. And then we again actually looked at this evaluation of snapshot ensembles against deep ensembles. And both papers were actually published at the same conference at ICLR 2017. So this is how publishing on archive goes these days. Here's a nice visualization of this procedure. So this here is a standard run of stochastic gradient descent. So it starts here, runs down there into a local optimum and finds this solution. And in our cosine annealing work, we actually do iterative stages of convergence. So we converge to this one local minimum and then to another local minimum and then to another local minimum. So this one and this one and this one. And then these are the snapshots for snapshot ensembles. As I mentioned before, this saves time during the training. So the training complexity is exactly the same as for a single training run. As we had with stochastic gradient descent with restarts, it was the same complexity of doing one long cosine annealing run. But you still have this k-fold overhead here in terms of memory and in terms of the time taken for predictions, so the latency, when you have k-ensemble members. All right, this brings us to the end of this video. And as always, I'd like to leave you with some questions. I encourage you to think about them, and I'll see you in the next video. Thanks.